In this lecture, we discuss section 4.5, Some Inequalities. Let's begin with theorem 4.5.1, the macro inequality. There are two hypotheses for these theorems. That is A, X is a non-negative random variables, and B, epsilon is a positive constant. Having these two hypotheses, we will have this conclusion. That is, the probability for the event x greater or equals to epsilon is always less than the expectation value of x divided by epsilon. The proof for these theorems is a good example to demonstrate how to solve problems using techniques that we have learned previously. The theorem that we need in this proof is theorem 4.1.3. Let's recall what is theorem 4.1.3. Okay. So in this theorem, we need two statements here. The first statement will be this: E of AS is equals to AES. Here, A is a constant, any constant, positive constant or negative constant, and S is a simple random variable. And the second statement that we need in this theorem is this: that E of 1A, the indicator function corresponding to the event A, so is equals to P of A, the probability of the events A. By using this theorem or the statement A and B, so we can prove theorem 4.5.1. Okay, let's look at the proof for these theorems. So to do this, let's look at several observations. Okay, first of all, this is our hypothesis. We always assume epsilon is a positive constant. Okay, so in this case, we have a first observation. We can observe that this event x greater or equals to epsilon is always of a subset of the sample space omega. So from here, then we can see that the indicator function for this event x is greater or equals to epsilon will be always less or equals to the indicator function with the event epsilon. And this, we know this is always equals to 1. So this is the first thing that we have. The indicator function corresponding to the event x greater or equal to epsilon is always less or equals to 1. So there, by using this observation, we can continue to the proof for these theorems. Okay. Okay, from here, we can see that one of this corresponding to this event, so this is always less or equals to 1. So we already know this. Okay, next, let's look at this. So we can see that if we refer to this event, x is greater than epsilon, then if we multiply the first term with epsilon and we multiply the second term with x. So since we restrict our discussion in this event, x is greater or equals to epsilon, so the first term must be less or equals to the second terms. Okay, and since we have multiplied x here, then we can also multiply x here. So x multiplied 1, and this is just equals to x. Next, what we need is we just need to consider the first term and the last term. So let's put it here. Then from here, we're going to have epsilon 1, x greater or equals to epsilon will be less or equals to x. So we have this inequality. Next, we're taking the expectation value for both sides. So since this is less than this, then the expectation value for the first term must be less or equals to the expectation value for the second term. So here, this is where we use the theorem 4.1.3. So then this, we can see that we can take out the constant, so epsilon, and then we have a E1 of epsilon this. So this is less or equals to EX. So the right-hand side remain no change. And from here, then this will become P of X greater or equals to epsilon. So again, the right-hand side, no change. So just for information, here we have used a theorem 4.1.3, part A, and here we have used theorem 4.1.3, part B. Okay, so after this, by shifting the constant epsilon to the right-hand side, then we obtain the inequality. So this is our result, the macro inequality. Before going through examples given in the lecture notes, let's look at another theorems. First, the theorem 4.5.3, the Chebyshev inequality. This is because its proof is actually quite similar to the proof of macro inequality that we have discussed just now. Okay, so since your memory is still fresh, so it will be better we look at the proof for this theorem first. Okay, let's look at the statements for these theorems. Next, we look at second. So theorem 4.5.3. Okay, so this is known as Chebyshev inequality. So there are altogether 3 hypotheses. So let's look at the statement. Suppose A, x is greater or equals to 0. Yeah, of course, here x must be have to be a random variable. Okay, and secondly, epsilon is a constant. So unlike the previous theorem macro chain, the epsilon need not be a positive constant. Yeah, it could be a negative constant or 0. And number 3, we need to consider another function, g. So which is a positive and increasing functions. By consider these 3 hypotheses, A, B, C, then we can have this conclusion. This is one inequality, that is the probability of x greater or equals to epsilon is less or equal to E of gx over G of epsilon. So this is the reason why we are requiring G is greater than 0. For otherwise, G of epsilon will be undefined. Okay, next, let's recall the meaning for this. What does it mean by G is increasing? So this is just simply means that whenever we have S less or equals to T, then we're going to have G of S will be less or equals to G of T. So that's the meaning for increasing function. I suppose you all have already known this. And again, we need to recall the same theorem that we have applied just now. First of all, E of AS is equal to A of ES. Okay, so same as the previous proof. And B, the expectation value for the indicator function 1A will same equals to P of A. Okay, by using all these properties, then we can now prove these theorems. Again, before we prove this theorem, so we need to look at several observations. First of all, we know this. When epsilon less or equals to x, so as we have mentioned just now, because of g is an increasing function, whenever s less or equals to t, g of s will be less or equals to g of t. Okay. When epsilon less or equals to x, then we must have g of epsilon will be less or equals to g of x. Okay, so this is because of the property g is an increasing function. Okay, now we can have a similar argument for it. Okay, again, we look at this same property. First, we look at it. The indicator function for this event x greater or equals to epsilon, this is always less or equals to 1. Again, this is because of the same argument, so this is always equals to 1 of the sample space. Okay, we know this already. Okay, next we look into this event. Yeah, x greater or equals to x. Okay, so because of, if we just restrict our discussion under this context, x is greater or equals to epsilon, then we can have g of epsilon will be always less or equals to gx. So that's why here we can have this inequality. G of epsilon is always less or equals to g of x, okay, because of the property up here. And since we have multiplied gx here, so we need to multiply gx over here. Again, same as the proof for the macro inequality. Now we only need to consider the first term and the last term. With the we have this inequality here. Then we're going to have g of epsilon multiplying the indicator function corresponding to the event x greater or equals to epsilon will be less or equals to g of x. Next, we use the same process. We are taking the expectation value for both terms. So this must be less than this. So again, we are going to use theorem 4.1.3a. Then we have this. We can take out the constant g of epsilon, and then it becomes e of this 1 of the event x is greater or equals to epsilon. So this will be less than. So the right hand side remain no change. That will be the expectation value for g of x. So again, so just a remark. So this is, we have used theorem 4.1.3a. And next, this one, we're going to use the theorem 4.1.3. So it becomes G of epsilon E of x greater or equals to epsilon less or equals to E of Gx. The right hand side remain no change. So this one, we have used theorem 4.1.3b. So actually, we just applying this statement for this parts only. And also, we are applying the statement theorem 4.1.3b on the left-hand side to get this. Next, we just need to shift G epsilon to the right-hand side. Then we obtain the inequality. So these two inequality are quite similar, okay, except there is one positive increasing function get involved in this Chebyshev inequality. Okay, that's the end for the proof. Next, we shall go back to the example in the lecture notes. Okay, let's begin with example 4.5.4. Okay, before this, that is a typo in this example in the lecture notes. Please make a correction for it. Okay. Okay, let's look at the original statement for these examples. Okay, so this is a statement in the example. Please make a correction. How should I say it? Okay, maybe what you can do is, please make a correction. So instead of Chebyshev inequality, so please change to Markov inequality. Okay, Markov inequality, and substitute this. Okay, maybe this is not substitute. Maybe we shall say we replace x with x minus mu square. Okay, and substitute. Okay, all right, so that's it. Okay, please make a correction for the statement in the lecture notes. Okay, so let's look at the examples. Let mu equals to ex, that is the main for the random variables, and as usual, sigma square to be the variance for the random variable x. For any positive constant k, so after replacing x with x minus mu modulus square, and after substituting epsilon equals to k square over sigma square in Markov inequality, we obtain another inequality here. So since this is just one of the special case for Markov inequality, therefore in some textbooks, this is also known as Markov inequality. Okay. In fact, this version of Markov inequality is actually a special case for the Markov inequality of our lecture notes theorem 4.5.1. Okay. Okay, let's look at the solutions for this example. Okay, before that, I think this is a little bit confusing by replacing x with x minus mu. So maybe what we can do is we just rewrite the Markov inequality by using another symbol we use y instead of x. Okay? So I think that will be much better. Okay, Markov inequality. So just change the symbol. So we're going to have a, instead of using x, we use y. P of y greater or equals to epsilon is always less or equals to e of y and then some epsilon. So this is Markov inequality. Okay, so we follow the instruction up there. So what we can do is, first of all, we have this. We have right as usual. Right mu to be the mean for the random variable. Okay, sorry, EY. And after that, we are taking sigma square to be the variance for y. Okay. And next, what we can do is we can take y to be x minus mu square. Okay. And after that, we can take epsilon to be k square over sigma square. So we are taking this in here. By substituting these two into the Markov inequality. Let's see what happened. Okay, we shall get back this inequality. By taking this, then we can have P of, so if we're taking epsilon to be this, k square sigma square less or equals to taking y to be the square of x minus mu. So this will be less than e of this x minus mu square over. So epsilon is k square over sigma square. Okay, so according to the definition, I think it's clear. So this is just the gradient for x. And according, sorry, I think this should be x instead of y. So this is a gradient of x. So that's why, according to our symbol, so this will be sigma square. Okay. So here we have square on both sides over this inequality. After cancelling the square, so we're going to have k over sigma less or equals to modulus x minus mu. So this will be less than. So I'm going to have a sigma square over k square over sigma square. So it ends up to be 1 over k square. So this is how we can get the inequality in the examples. Right. Okay, let's carry on with example 4.5.5. So in these examples, we consider x is a uniform distributions over the interval 0, 1. So what does it mean? So this one means that the PDF will be given by fx is equals to 1, where x is in between 0 to 1. So I think it is not, this is standard distribution. So we already know the mean will be 1 over 2. This is actually the EX, okay? The mean for X will be this. And also we know the variance will be 1 over 12. The easy calculation. That is the variance for x. So again, this is the inequality that we can have just now. So in our previous example, maybe I can state the inequality over here. So that is P of x minus mu greater or equals to k sigma will be less or equal to 1 over k squared. So this is actually from example 4.5.4. Okay, so we're going to apply this inequality into this case here. Okay, let's carry on to this. So we look at here, P of x minus half greater or equals to 1 over square root of 3. So according to here, so half is our mean. So therefore, this is actually equals to x minus the mean. So the variance is 1 over 12. So from here, then we can see the standard deviation will be 1 over square root of 12. So that's why if we want to put it in this form, so we have to make sure that is a terms 1 over square root of 12 inside. So from here, we can see this thing can be written as P of x minus half greater or equals to. So in order to make 1 over square root of 2 inside, so then we just multiply 2 over 2. So that will be 2 multiplying 1 over square root of 12. And this is actually 1 over square root of 3. So now everything is clear. Then this is our mu. So this thing will be our sigma. And we can take this to be k. So from here, then we can see this whole thing will be less or equal to P of, not P, sorry. Okay, so if we're following this, so the right-hand side will be always 1 over 2 squared. So that means this is just the 1 over k squared. So this is how we can get the solution. So this is 1 over 4. So it's not hard to solve this problem if we know the inequality from the previous examples. Okay, next we look at more challenging examples over here. So example 4.2, 4.5.2a. Okay, there are 2 hypotheses in these examples and 1 conclusions. Okay, maybe I put it this way. So in this example, so there are 2 hypotheses. A, again, x is non-negative random variables, and B, the mean for x is equals to 0. So from these 2 hypotheses, A and B, then we have this conclusion. P of x equals to 0 is equals to 1. So 2 hypotheses, 1 conclusions. Okay, let's recall some of the techniques that we need to solve this problem, as well as some of the observation that we can derive for it. Yeah. Okay. First of all, so if you look at here, we are considering this event x equals to 0. Okay. So first of all, we know that the event x equals to 0 is equals to actually the complement for x greater than 0. So this is true because of x is always greater or equal to 0. So this is true because of x is always greater or equal to 0. So this is because of x is always greater or equals to 0. So we don't have to consider the value for x is negative. Okay, so this is the first observation that we can have. And next, we can have this. Now we are looking at this, the event that x greater or equals to 0 can be written as the union of this event, k greater or equals to 1 over k, where k running from 1 to infinity. And next, we can see, we just simply write this as ck. Let's say ck. We just simply make it easy, write this one to be ck. The event x greater or equals to k. So we can see that this event is increasing. Okay, so I think this is quite straightforward. Okay. So if you really want to evaluate, so maybe we can look at the first few terms. So let's say you look at C1. C1 is, okay, maybe I just write. Just look at the first event. So when k equals to 1 will be x greater or equals to 1. So if you are looking at this 0 and to infinity, okay, so that will be up to here. So this is C1, right? Okay, next, when k equals to 2, so we are having this. So when k equals to 2, so the event C2 will be x greater or equals to half. So again, so that means if you look at the line, so this is 1. So that will be up to here, right? So this is half, this is 1. So that will be up to here. And so on. So from here, then you can see this is always smaller than this. So that's the reason why this is an increasing sequence of event, right? So this is how we can get the third observation here. Okay, next, we need to recall a general result. So recall a general result, theorem 1.4.3. So you may refer back to chapter 1. So the statement for this theorem is this. If ck is an increasing sequence of events, then limit of pck when k approaches to infinity, which is just equals to the probability of the union of all the ck, where k running from 1 to infinity. So if you look at all the things here, if we are taking ck to be this event, so the union of ck will be just equals to this. Okay. So having all these observations, then we are ready to solve or to prove these theorems. Okay, so now what we need to do is we just need to write down what we have observed on up there. Okay. So first of all, we look at this event. Since maybe make it easy, we define the event ck to be 1 over k. Let's go inside. So this is an increasing sequence of events. Okay, first of all, we have this. And we know that we're up there. And next, we know that the union of all the ck is actually just equals to this. I think maybe I give you the full, instead of being ck, I think I better put a full one. So the union of all this k greater equals small k. So this is just equals to the event x is greater or equals to 0. So hence we know we must have this P of x greater than 0 must be equals to limits of k to infinity of P of this. Okay. So how to get this statement? So this is actually the last observation here. That is, we are applying theorem 1.4.3. So maybe just to give you a remark. So this is, we are using theorem 1.4.3 over here. Okay. Okay. So let's say we stop here. Let's say we have a statement 1. Okay. So next, what we can do is we continue. We take epsilon equals to 1 over k in Markov inequality. So again, what is our Markov inequality? So maybe I'm going to put it over here. So our Markov inequality is like this. P of x greater or equal to epsilon will be less or equals to E of x over epsilon. Okay. So if we put epsilon to be 1 over k here, then this is what we can have. We're going to have P of x greater than 1 over k will be less or equal to E of x over 1 over k. Okay, we're just substituting our epsilon here. Okay, next, we just go back to our hypothesis. From our hypothesis B, Ex is always equals to 0. Okay, Ex always equals to 0. The mean is always equals to 0. So then we look at here. Then from here, then this is always equals to 0. So this is nothing. This is just by the hypothesis. Yeah, so this is always true by the hypothesis. Okay, if this is 0, then this is implies that limit k for p of 1 over k will be always equals to 0. Okay, or actually we don't even need this. So this is always equals to 0 for all k. Number 2. Okay, now we comparing these two statements. P of the event x greater than 0 will be equals to the limit of p of k greater or equal to 1 over k. However, in the statement 2, we know that p of x greater or equal to 1 over k is always equal to 0. Then from here, we must have this. P of x greater than 0 must be equals to 0. And this is equal to 0, then we can see, or P of x equals to 0 must be equals to 1. Okay, because of this is just the complement for it. Okay, as we have observed just now, this is just the complement for these statements. Okay, so this is how we can prove our statements here. Likewise, maybe before we continue to the next example, so let's go back to all the observation or all the technique that we have used to prove these theorems. Okay. Okay. First of all, let's look at our hypothesis here, or the statement for our examples. So two hypotheses: x is non-negative random variables with 0 mean, and the conclusion will be P of the probability of x equals to 0 must be equals to 1. Okay. So that means, okay, we have this. So let's look at here. What are the techniques that we need to use? Basically, the main result or main technique that is needed in the proof for this theorem will be theorem 1.4.3. That is, if ck is an increasing sequence of events, then the limit for pck will be p of the union of ck. Next, what we need to do is we just need to construct our ck for these examples. Yeah. So this is our observations. Okay, first, the event x equals 0 will be the complement for x greater than 0. Yeah? And the second observation will be the event of x greater than 0 is equals to the union of all these events, x greater or equals to 1 over k. And next, we can see that these events, x greater or equals to 1 over k, is an increasing sequence. Yeah. So by using 1, 2, 3 together with this theorem 1.4.3, then we tidy up the argument. So this is the proof for it. Okay. Next, we proceed to the second part for the example. So example 4.5.2b. So again, there are two hypotheses and one conclusion. So the first hypothesis will be, again, x is a non-negative random variable. And secondly, E of x is not infinity. Then the conclusion will be P of x equals to infinity will be equals to 0. All right, so again, the main technique that is needed will be these theorems, the same theorem. However, the other version for this theorem, that is, supposing we have a decreasing sequence of event bk, then the limit when k approaches to infinity for p of bk will be equals to p of the, sorry, this is not union, the intersections of all the bk. So which is quite similar to the previous versions. So in this case, the main idea is we need to construct a suitable bk over here and apply into our situations here. First of all, we know that the event x equals to infinity is actually equals to the intersections for all these events, x greater or equals to k. And secondly, we know that this event, this sequence of events, x greater or equals to k, is decreasing. So let's check whether this is true or not. Okay, so you can easily check when k equals to 1. Okay, when k equals to 1, that will be x greater or equals to 1, right? So, okay, let's say this is 0 and it go up. So let's say 1 is here. Okay, then that will be this part. X greater than 1, right? Okay, we carry on to when k equals to 2 will be x greater than 2. So we look at the same x-axis. So 1 is here, then 2 is here. So x greater than 2, so that will be 2 onwards. So I think it's clearly this portion must include this, right? So therefore, this will be smaller and this. So similarly, you can go to x greater than 3 by looking at the same arguments here. So I'm going to have 1 is here, 2 is here, and 3 here. Okay, so that means it covers these portions on it. So this will be belongs to here. So by using this argument, then we can see that, yeah, this is true. So pk must be decreasing. So since we have a decreasing sequence of events, then we can now apply this theorem 1.4.3 to our case here. Okay, we have already gathered all the techniques that are needed, as well as the observations. Okay, now we can look at the solutions for it. Okay. So the solution is actually quite similar to the solution in part A. So first of all, we look at it. First of all, the event, the sequence of event x greater or equal to k is decreasing. Okay, and also this event x equals to infinity is actually just the intersection of all these events. So we must have this. P of x equals to infinity is limit of k approaches to infinity for P of x greater or equals to k. So again, we have statement 1. Okay. So again, how to get this? So this is by theorem 1.4.3. Okay, as we have mentioned just now. So again, let's recall our Markov inequality once again. So this Markov inequality, the statement will be like that. X greater or equal to epsilon will be less or equal to E of x over epsilon. So this is our Markov inequality. So what we can do is we just need to take epsilon equals to k in our Markov inequality. So if you look at here, then this is what we can have. P of x greater or equals to k will be less or equals to E of x and 1 over k, right? We are just putting epsilon to be k. Okay, now this is what we need to use. By using 1, this is equal to this, right? Hence, we're going to have P of x equals to epsilon will be equals to limit of k to 1 over k, yeah, by statement 1 and statement 2. So this is statement 2. So maybe I should say by using 1 and 2 here. So this is equals to this. Okay, now the crucial one will be this. What is our Ex here? So let's go back to our hypothesis. So the hypothesis said that Ex is not infinity. So this is very important, yeah. And because of Ex is not infinity, so this must be equals to 0. So this is because Ex is not infinity. Okay, this is what we have. So that's the reason why we need to impose this hypothesis that Ex is not infinity. So this is how we can solve these examples here. Okay, we have discussed, okay, maybe just a summary. So we have discussed two inequality. Okay, so that is the first one will be the Chebyshev inequality. The second one will be the macro inequality. And also, we also discuss some examples. Okay, so let's say the applications of this inequality. Okay. So next we move to another examples. Okay, no, sorry, another inequality. Next we discuss another inequality, that is the Jensen inequality. Okay. Okay, before we discuss this Jensen inequality, so we need to have one concept, so-called the convex function. Okay, I'm not going to look at the proper definition for the convex function here. Okay, you guys may refer to the lecture notes. Okay, here I just give you the geometric interpretation for what is meant by a convex function. Okay, so what is a convex function? Or maybe I should say this: how a convex function looks like. Okay, how the convex function looks like. So a convex function will be looks like this. Graphically will be like this. So let's say you look at a graph, the curve will be looks like this. So it's always like this. Okay, or like this. Okay, so as long as, how should I say it? This is the convex function. The idea will be like this. So a convex function is a function having this property. That is, you just simply pick 2 points. Okay, so if you draw a line here, so this green color line is always above the red color line. Okay, same as here, or equal. If you draw 2 lines here, so you draw a straight line connecting these 2 points. So the green color one will be always above or identical with the red color curve, original one. Right? So this is the idea for a convex function. So therefore, this is an example of convex function. So this is an example of a convex function. Right? So the idea, maybe I just simply write the ideas over here. What is meant by a convex functions? Okay, so if you pick any pair of points on the curve, okay, if you pick any pair of points on the curve, and when you draw, okay, maybe I will say this is the red color one. Okay, when you draw a straight line connecting these 2 points, the green color one, okay, maybe I would say the green color one. I will say the green line. Okay. Okay. So if you pick any pair of points on the original curve, the red color one, and when you draw a straight line which connecting these 2 points like this, so point A and point B, okay, point A and point B, the green color one. So then the green color line, has to be above the red line. So a convex function is a function whose graph will have these properties. Okay, so geometrically, a convex function can be described in this. So as you can see, you can pick any pair. So maybe here and here, you draw another line. So the green color straight line connecting the 2 points must be always above the original curve, the red color one. So that's what this is also maybe not above, must have to be above, what do you say, or identical or same as the red one. Okay, either above or identical. So once the graph for the function has this property, so it will be a convex function, right? So I'm not going to write down the actual definitions. So if you want to look at it, so you can see definitions 4.5.6 for the proper definitions of convex functions. Okay, so I'm not going to write down over here. Okay, so if you want to look at the proper idea, rigorous definition, you may look at this definition 4.5.6. So however, here I just demonstrate the idea. So this is the picture over here. Okay, so the picture for a convex function must be always looks like this. So how's the graph for a non-convex function looks like? So that is very simple. As long as the graph doesn't look like this, so that is non-convex. Yeah. So just to give you examples. Yeah. So these 2 are the convex one. So I give you an example for the non-convex one. So if you look at a graph, so let's say graph, just one examples. Okay, so this one. Okay, so this is one of them. Another one. Okay, maybe look at this. Right. This. Okay. These 3 are not convex function. Okay. So this is not convex function. This is not convex function. Okay. That's a very simple example. Sorry. Okay. I hope after this you guys have some idea how the convex function looks like. Okay. So because of the original definitions, it's not that easy to be used. So therefore, no point we look at the original definitions. Okay, so we look at a special case or special types of the convex function. So for this special type of the convex function, then we have a very simple criterion for us to test whether it is a convex function or not. Okay, so that is a statement given in this proposition 4.5.1. Okay, so this is a test for a convex function, test for convexity for twice differentiable function. Okay, we only need one hypothesis. Okay, suppose f can be differentiated. Okay, that means it's differentiable for 2 times. Okay, on the interval I. Okay, so that is the hypothesis. It can be differentiated 2 times. Okay, some function might not be able to differentiate 2 times. So as long as the function can be differentiated for 2 times, okay, then we can have this conclusion. Then f is a convex function if and only if f double prime is always positive on the interval. So that is very simple. So we just need to check the sign for the second order derivative for the function. So if the second order derivative function is always positive, then it must be convex. Okay, since most of the functions that we discuss are smooth almost everywhere, that means it can be differentiated for 2 times almost everywhere. So that's why this criterion is very useful for us. Okay, okay, let's look at several examples. Okay, several simple examples. Okay, A, we look at, let's say we look at fx is equals to ex. Is this a convex function? Because we look at the interval R. Okay, so we can check. In this case, f double prime, so you're differentiating 2 times ex, so this is always positive, right? So which is, maybe we can say, if we differentiating 2 times, so which is also equals to ex, so this is always positive on R. So hence we can say that hence f is convex on R. Okay, we look at another one B. So let's say fx is x power of 6 on R. So you can see you're differentiating 2 times. So 6 times 5 will be 30 x power 4. So, oh, okay, sorry, I think this is not a good one. Maybe x squared, better, easy. So f double prime. So that will be 2, so it is greater than 0 on R. So hence, it must be convex function. And if we look at number 3, C, fx is x power 3 on R. So we can see f double prime will be 326x, right? Okay, so we can see this is less than 0 when x less than 0. Okay, so we can see hence f is not convex on R. Okay, so at least as you can see, this proposition is a very simple technique for us to test whether a given function is convex or not. Okay, now it's time for us to look at the statement for the main theorem that we want to look at it. That is the Jensen inequality. So that is theorem 4.5.7. So this is so-called the Jensen inequality. Okay, so there are these hypotheses. So suppose A, G is a convex function. And B, X and E of Gx integrable. What's the meaning of integrable here? So that is what we're discussing. So the main is so that means both Ex and Eg of X exit. Okay, exit means which is not plus or minus in effect exit. Okay, that means so once we have these two hypotheses, then we can have this inequality. Then G of E of X will be less or equals to E of G of X. So this is true when G is a convex function. Also, we also require that X and sorry, I think this one we do not need E here. Ex and Gx, G of X. X and G of X are integrable. So X and Gx are integrable means E of X and E of Gx exit. So when having these two hypotheses, so we have a conclusion. So the most important hypothesis will be here, G is a convex function. Then we can have this. So let's look at simple examples for this inequality. Okay. Let's look at example 4.5.6. So this is the one. If X and Ex are integrable, then we have this. E of X less or equals to ln of E of Ex. Okay, what we can do is we just need to construct a convex function and then we apply the Jensen inequality here. So what we can do is first we can take G of X to be Ex. Okay, then we can see this. Then G is convex, right? So as in the previous examples, okay, we have already discussed when Gx is Ex, G is a convex function. So when G is convex and X and this is actually, you can see this is actually our G of X, right? So X and Gx are integrable, then we can apply the Jensen inequality. So apply the Jensen inequality, we have this. G of Ex will be less or equals to E of Gx. So however, G of X is E of X, right? So therefore, this will becomes E of ex. Exponential of ex will be less than e of exponential of x. Okay, now we can taking ln both sides. So then we can have e of x will be less or equals to ln of e of exponential x. So this is how we can get this inequality.